Let's now wrap up this lecture by comparing the two loss functions we just finished studying in quite a bit of detail algebraically, and what lessons we can draw from these as we start setting up the stage for the next part of the course. So in here, we have a comparison of what the loss surface looks like for our little toy data sets for both of the losses we looked at carefully in the last three segments. So we call the loss surface the plot of the loss as a function of the parameters theta. In our case, theta was a one-dimensional parameter, so the loss surface is just a line. If we had theta 1 and theta 2, two parameters, or theta 0 and theta 1 as we tend to call them, then this would be a 3D plot of a surface as a function of two variables, right? And beyond that, if you have a three-parameter model, obviously it's not possible to easily visualize that surface anymore, and beyond three parameters, that's impossible. You can imagine that, as we described earlier, there are today in practical usage in machine learning models with millions of parameters. Visualizing loss surfaces is impossible. However, it's very useful to work on these one and two dimensional cases because a lot of the intuition that we gain from these low dimensional settings does apply and is useful for certain aspects of the high dimensional problems. So this is still valuable learning that we're doing here. So as we saw, for the L2 loss, the minimizing value was at 25 at the mean of our data set, whereas the L1 loss was minimized at the median value of the data set, which for these particular data was at 22. So we see that these two losses lead to different values. Notice, however, the vertical scale of the two losses is wildly different. And this should be pretty obvious. For any given observation, this is ignoring sign. The single value L2 loss is the square of the single value L1 loss, right? And so in general, you're adding up, this curve is made up of adding squares, the squares of these values. So it's no surprise that the values do get much larger. Outside of zero, they both have a minimum value, but outside of the minimum value, it's not a surprise that this one is larger. In general, across loss functions, comparing values doesn't really have any intrinsic meaning. So the value of the loss function doesn't have intrinsic meaning in terms of physical units so that you can compare in any practical sense these two. Now, it is possible to construct loss functions that combine L1 and L2 terms in a single algebraic expression. If you do that, you do have to be careful about these value discrepancies and potentially think about whether your data needs any particular kind of scaling, whether it makes sense to add units of the data and squares of the data. So these are questions that we're not going to deal with in the context of the course right now, but at least I want you to keep in mind that at first you should think of these only as relative values to compare. So it only matters whether you're minimizing within one rather than connecting two loss functions. But if you get into the business of constructing complex loss functions that include more than one algebraic kind, then you need to think about those values and whether that makes sense or not. Now, these two types of measuring error, these two loss functions, the mean squared error and the mean absolute loss, are similar in some aspects, but they're also different. And they basically make different trade-offs. Every loss, there is no such thing as the correct loss function. They simply have different trade-offs. So the mean squared error is what leads to the sample mean, as we saw already. And it is a very smooth function. We see that in the plot, but we also see that algebraically. It's in general a parabola or a paraboloid in more than two dimensions. It's easy to treat analytically. The calculus was fairly straightforward, and it's also, because it is so smooth, numerical methods also work very well for this kind of function. It's nice, convex, and smooth. So computational machinery is kind of happy with this kind of function. On the other hand, the sample mean is very sensitive to outliers. So if we take one observation and we say add 1,000 to our largest observation, the optimal value, the sample mean, would become 225 instead of 25, meaning one single data point that is very different would change the value of the sample mean dramatically. There's a good example that I like to think of to illustrate this. Imagine you take a room of 1,000 people sampled, say, from campus, students, administrators, faculty, and you ask, what is the mean income of the people in this room? You're probably going to get a number somewhere in the neighborhood of 5 or 6 figures. Now imagine that to that group of people, you add, say, Bill Gates or Jeff Bezos or some other multi-billionaire. The sample mean jumps immediately because of that single extra person. The sample mean is going to jump to a value in the probably in the hundreds of millions, right? Because now you have, or at least in the many millions, because now you have this one data point that is extremely large. So the sample mean is very sensitive to even one person. So you would say the average wealth in the room is now tens or hundreds of millions, whereas everybody else is still the same. It's just that now we have one multi-billionaire in the room. The sample median, on the other hand, is not sensitive to that. So the mean absolute error leads to a model where the resulting optimal value is robust to outliers. Adding one very large value to say, the largest observation doesn't change the median at all. And so that is what we mean when we say that the sample median is robust to outliers. On the other hand, if we look at the loss surface, we see that it has these kinks, these points where the loss function is continuous, but it bends sharply. And what happens is at those points, there are no derivatives. The derivative is not well defined because the limits coming from the left and the right are different. Now, analytically, we were able to handle that. The algebraic expressions were simple enough that by breaking up our sums into or across those boundaries, we were able to reason through this non-analyticity of the function and still get an answer and land on the definition of the sample median. We were able to do the calculus. On the other hand, a computer isn't looking at the analytical expressions, it's just trying to work its way through the data, and the computational algorithms that we use for optimizations need to compute derivatives. So things that don't have good derivatives are going to make life hard for numerical algorithms. And so these kinks right here that seem somewhat innocuous and that we were able to reason our way through algebraically are going to make life difficult for the numerical algorithms. So in that sense, these two loss functions that are kind of the basic workhorses have sort of contrasting trade-offs. They trade off smoothness for robustness. And you can imagine ways of mixing and matching them, and those such things do exist, but we're not going to get into that for now in the course. So in practice, you get to pick your loss function. You have to think of these trade-offs, and that's the big lesson of today. So let's summarize quickly what we learned today. We sort of looked at the modeling process as something based on 3 broad steps, and these 3 steps are a good way of thinking throughout the rest of the course. When we have a data set, after we've looked at the earlier phases of the data science lifecycle, we have to pick a model. Today, we focus for simplicity, just to illustrate the process, on the simplest imaginable model, which is a constant, predicting one number out of the data. And so once we have defined those parameters, then we have to explore how to compute them. We remember today we looked at parametric models, but we've also mentioned models like KDEs that don't have explicit parameters in them. They may have hyperparameters, but they don't have parameters that you compute that you can compute from the data. But for models that do have parameters, let's say one like today, or the ones we will then encounter in the next lectures that have more than one model, we now have to ask, well, how do I find that value? And we do so by defining a function. So the model is the structure of what is it that we're going to compute about our data. The loss function says, how are we going to define what is a good value, right? We need to encode what do we mean by good in the loss function. We looked today at 2 of them, the squared loss and the L1 loss. There's others. That's something that you get to pick, and you get to balance the trade-offs, which we just saw in the previous slide. And finally, you have a model. You've decided how are you going to measure what do you mean by good, and then you try to make it as good as possible. As good as possible is called optimizing, or in this case, minimizing, since the optimal value is low. Sometimes optimizing means maximizing a function. So for the case of loss functions, optimizing means going to the minimum of the function. So now we try to minimize the average loss across the data set. So the loss function as a function is defined first on one point. We then define the empirical risk, or the average loss, across the entire data set. And then we find the optimal value by minimizing that loss function. This last step is what we call fitting the model. Fitting the model is the term of art for saying I want to minimize the loss I defined to find the optimal values of the parameters that give me that loss, that minimal loss value. And remember, the thing you're after is the parameters. The actual value of the loss function is irrelevant, and in most cases you only plot the value of the loss to see what is happening as your model improves, but you don't really ultimately care about that. The specific value, as we said, doesn't really encode too much meaning. So as a vocabulary review then, to wrap up, the average loss when we use the L2 loss is called the mean squared error. Squared loss and mean squared errors are not the exact same thing. Squared loss is the definition of the function per observation, and mean squared error is the average across the entire data set. So one is made of the sum of the others divided by n. And same thing for L1, the L1 loss and the mean absolute error. Now, these two new terms, mean absolute error and mean squared error, are connected with things you already knew. As we saw, the mean squared error is what leads you to the sample mean. So the sample mean is that magical value of theta that minimizes the mean squared error, and the sample median is the value of theta that minimizes the mean absolute error. So this is a really important lesson at this point in the course, which is that you've now gained a new insight into these two quantities. You can obviously define what is the mean of a set of numbers, add them up and divide them by n. What is the median? Find the midpoint observation, and that is the median for the data set. Those are definitions, and they're perfectly valid. Now, the question is, why did we define those quantities that way? This gives you some insight into the value those quantities have. It turns out that we didn't pick those definitions arbitrarily. They happen to correspond to the quantities that are optimal for a specific definition of a loss function. So you now have a new insight into a connection between modeling and loss functions and model fitting and descriptive statistics, so descriptive summary statistics that you already knew. And finally, as we mentioned, for the purposes of this course, we will consider average loss and empirical risk as synonyms. Today, we've been using only these two functions, the MSE or the MAE, but in general, this connection remains true for any loss function that we may use. Now, in the next few lectures, what we will do is we will go beyond, we will keep kind of the same framework we just covered today, but we will go beyond the very simplistic constant model, and we're going to introduce the simple linear regression model that you already have seen in Data 8, but we will look at it in a more complex setting, and we will also look at other kinds of models, such as multiple regression, logistic regression, decision trees, and random forests, which will come later. And we will also introduce other loss functions beyond the L2. We're going to use the L2 loss quite a bit, but we are going to introduce new loss functions that are more appropriate for other kinds of models, and we will see why the L2 loss is not the ideal choice for every setting. And it's not just because of outliers. It turns out that for other problems, there's other reasons to go beyond the L2 loss. And we are going to also need to appeal to more sophisticated computational techniques for the step where we fit the model. So for each of the three levels of the process that we saw today, defining the model, defining the loss, and fitting minimizing the loss, we're going to go beyond what we did today. And for the model fitting, the handwritten algebraic techniques we use today will not be sufficient. So we're going to encounter situations where we need to appeal to computational techniques like gradient descent. So that concludes our introduction to modeling. This now opens up, in a sense, the rest of the course to all of these sophisticated techniques that will help you make decisions based on data. The concepts we introduced today are extremely important. We're going to revisit them over and over and over. So please go over this lecture carefully. We had a mix of lectures for this session, and ask us questions if anything isn't clear, because these are sort of really bedrock concepts for the rest of the course. Thank you.